In this problem, we're being asked to calculate the bond energy between sodium and chloride ions. We're being asked to report them in kilojoules per mole of bonds. We're going to assume that the bond is purely ionic, such that the positive charge from the sodium is attracted to the negative charge of the chloride. This force of attraction is equal to 1 over 4 times pi times the permeativity of free space multiplied by the distance between the ions squared. And we're going to multiply this by the absolute value of the valence electron charge multiplied by the charge of one electron. We're going to do the same thing for the second ion. We've got Z2 multiplied by the charge of one electron. The value of epsilon naught is just a known constant. It's equal to 8.85 times 10 to the minus 12 farads per meter. In base units, a farad per meter is equivalent to a coulomb squared divided by a joule times meters. And because we're dealing with a bond between a sodium plus and chloride minus 1, the value of Z1 is going to be equal to positive 1 and Z2 is equal to negative 1. The negative 1 is going to cancel out because we're looking at the absolute values of these. So in essence, we can substitute in the positive 1 and minus 1 and we'll just find that this is equal to E squared. And the value of E is equal to 1.602 times 10 to the minus 19 coulombs. This is the charge on one electron. So at this point, if we knew the bond length, the value of R, we could go ahead and plug numbers in carefully with the units and we could solve for the force of attraction. To do this, though, it's important to think about the radii between the elemental sodium and the elemental chloride. If you looked at those values, you would find in the periodic table that sodium atom is larger than a chlorine atom. However, sodium, when they bond, the sodium valence electrons are transferred to the chloride. And what we're left with then is sodium plus 1, chloride minus 1. If we look this up, the radii for these, the radius for the sodium cation is equal to 1.02 angstroms, and that of chloride is actually larger, it's equal to 1.81 angstroms. Converting these to meters, we multiply both of these by 10 to the minus 10 meters. 1.81 times 10 to the minus 10 meters is the radius of a chloride anion. And the value of R is just the sum of these two, and we get a value of R that is equal to 2.83 times 10 to the minus 10 meters. Substituting all of these in, we get a force of attraction equal to 2.88 times 10 to the minus 9 newtons. A very small attractive force, of course, because we're just dealing with the attractive force between two ions. Well, we're being asked to find the energy of attraction, which is equal to the integral of the attractive force multiplied by dr. So when we integrate the force of attraction, what we're left with is a negative value, negative 1 divided by 4 pi epsilon naught times r, multiplied by the charge of one electron squared. The negative sign here refers to the fact that the energy level between the sodium and the chloride ions is 0 when they are far apart. We've got an attractive force. As these ions come together, their energy levels drop, and at the minimum value of energy, they reach their equilibrium bond length. Note that what I am omitting in this calculation is any sort of repulsive force. So we're just going to assume when they reach their radii that the energy level is at a minimum. If I plug in numbers here, what I'm going to come up with is a value of 8.2 times 10 to the minus 22 kilojoules. And that's the energy associated with one bond. If I multiply this by 6.02 times 10 to the 23rd, Avogadro's number, what I come up with is a value of 490 kilojoules per mole of bonds. And this is slightly different than the published value of 640 kilojoules per mole, primarily because this bond isn't entirely ionic and because I'm neglecting any sort of repulsive energy associated with the bond. But the take-home message here is that with these very simple assumptions, I can come up with something reasonably close to the published value.